The last colligative property we want to discuss is the osmotic pressure. So if we have two solutions separated by a semi-permeable membrane, one solution has a low concentration solute, and the other solution has a high concentration solute. What's going to happen is that solvent is going to flow through a semi-permeable membrane from the more solvent to the less solvent. And this process is called osmosis. So during osmosis, the solvent particles, they flow through a semi-permeable membrane to bring the two solutions closer to equilibrium, to bring them to the same concentration. So this is actually what's happening in there. The second solution will decrease in concentration by a certain height of the solvent, so that you will have now the two solutions having the same concentrations and equilibrium is reached. This is called osmosis. This is another illustration of osmosis. So you have a low concentration solution, and inside you have a high concentration solution, and you have a separation of a semi-permeable membrane. Always osmosis is the passage of the solvent, okay, from the less concentrated to the more concentrated, so that the more concentrated now will be diluted and the system will reach equilibrium. So both solutions will have the same concentration. Guys, we can stop this. This can be stopped. We can prevent that by simply applying an osmotic pressure. So what is the osmotic pressure? Osmotic pressure is the pressure that is necessary to prevent or stop the osmotic flow of the solvent into the solution. So we call it osmotic pressure, and this is represented by pi. There's a relationship between pi, the number of moles, the molarity, the gas constant, T is the temperature, and I is the number of ions in the solution. We said that if their solution is non-electrolyte, this is non-electrolyte. This means that you don't have an ionic solution. So your solute is not non-ionic, so it does not dissociate in the solution. So this is non-electrolyte. Then this means that I is equal to 1. And if your solution is a strong electrolyte, this means that your solute dissociates completely into individual ions. So I is equal to the number of ions, and I is always the Van Hoff's factor. M is the molarity of the solution. R is the gas constant, because we're talking about the osmotic pressure there. So there should be a gas constant, and the gas constant is either expressed in torrs or it's expressed in the atmosphere. Guys, it really depends on the units that you are calculating the osmotic pressure in. Is it in torrs or is it in atmosphere? So just pay attention to the given and to the question, okay? The product of the I and the M, this is called the osmolarity. Sometimes if you look at the equation, the osmotic pressure equation, they give you in the given both the osmolarity. Instead of giving you the concentration and the I, they just give you the osmolarity value. So this is the product of I times M. Let's have an example over here. So calculate the osmotic pressure. Now, normally, if they do not specify the unit of the osmotic pressure, normally what we do is we go by the osmotic pressure in torrs, not in atmosphere. So we're going to use the value of the R to be 62.4 liter torr per Kelvin mole. If they specify and they say it's an atmosphere, then calculate it in atmosphere. If not, just go ahead and use it in torr, you guys. So calculate the osmotic pressure of glucose. So we know that glucose is a sugar, and that sugar forms sugar molecules when it is dissolved in water. It is not ionic. This is not ionic. It's a non-electrolyte solution. So we would say that glucose is sugar, and the glucose is non-electrolyte. And if glucose is non-electrolyte, then this means that I is equal to 1. Okay? So if I equal to 1, then let's go ahead and substitute. So they need the osmotic pressure, so they need pi. I already have I, which is equal to 1, times the concentration. So I am given the concentration, which is 1 molar. So I'm given that. I am given the temperature. Basically, I'm given everything in here. I know what R is, and I am given the temperature. Guys, temperature is always in Kelvin. So if you are given the temperature in Celsius, please change to Kelvin. So let's go ahead and substitute. I is 1 times 1.00 molar times the R, which is 62.4. This is liter, torr, Kelvin, mole, times the temperature, which is 300 K. See, notice the units are the same, and you're forced to have the temperature in Kelvin because the R is in Kelvin. You cannot change the R, okay? R in both units, whether in atmosphere or torr, it is in Kelvin. So that is 18,720 torrs. This is the pressure that is required. This is the osmotic pressure that is required to stop the flow of the glucose. Okay, this is 18,720, and it's going to be torrs. We know that the concentration is molar, right? And let's go ahead and put the molar. The molars is moles per liter. So what we're doing over here, we are taking the liters out, we are taking the mole out in there. Pretty much we are taking the Kelvin out, so this is why we are left in the torr unit. Let's have another example. So a solution of an unknown substance in water at 293 Kelvin gives rise to an osmotic pressure of 5.66 atmosphere. So notice here, like they gave you the pressure in atmosphere, right? This is the osmotic pressure in atmosphere. What is the molarity of the solution? Okay, so they give you the osmotic pressure in atmosphere, right? So if they give you the osmotic pressure in atmosphere, you gotta change it into torrs. Why? Because we're gonna use R in torrs. You could keep it, by the way, in atmosphere. This way you have to use the R in atmosphere. So just pay attention to whatever you are doing. Since they did not bind us to since they did not mention anything about the units in there, so you either can keep the unit in atmosphere or change it to torrs, whatever you want. I'm just gonna go ahead and change that to torrs. Since it is this is an unknown solution of water gives rise to an osmotic pressure. So I know that water is this one is a weak electrolyte, so I'm just gonna go ahead and consider that as a non-electrolyte solution because there is no information about the solute. It's just water, so there's no information about the solute in there. It's just they gave you information about the solvent. So we're gonna go ahead and say that this is a non-electrolyte case since there's no information about the solute. So since there is no information about the solute, about the solute, we're going to consider this a non-electrolyte case. And if it is this is electrolyte case, this is a T. And since it's non-electrolyte case, then we're going to consider I to be equal to 1. So pi is I times the concentration times R times T. So what do we want? We want the concentration. We want M. This is what we want in there. So let's make an equation for M. So M is equal to pi divided by R times I times T. Okay? We can change the osmotic pressure from atmosphere to torr. So let's change the atmosphere to torr. the osmotic pressure. So we're starting with, what was that? It's 5.66 atmosphere. So 5.66 atmosphere times, I know that 1 atmosphere is 760 millimeter Hg, right? I cannot change to torr directly. I have to change to millimeter mercury and then to torr. So I know that 1 atmosphere is equal to 760 millimeter Hg. And I know that 1 millimeter Hg is equal to 1 torr. And this is how you change from atmosphere to torr. So you cancel the millimeter Hg, you cancel the atmosphere, and the answer is 4301.6 torrs. Okay? The reason why I changed the osmotic pressure into torrs, because I want to use the R in torrs. You could have kept it in atmosphere and used the R in atmosphere. So just pay attention to whatever R you are using, okay? So, and you're going to get the same answer in there. So it depends. Do you want your, it depends. Anyways, you're going to get the same answer in here. So this is going to be torrs divided by 1 times the R here, which is 62.4. This is liter torr K mole times 293 Kelvin. The temperature here that they are saying, this is 293, so this is what we are going to use. Okay, so here you go. Torrs and torrs cancel out, K and K cancels out. We're just going to be left with liter mole. This is it. So this is what we're going to be left with. As mole per liter, and our answer is going to be 0.235 molar. Again, you're going to get the same answer if you keep the pressure in atmosphere and you use the R in atmosphere as well, which is 0.082. Let's have another example. This is similar to number 28 in your homework. What is the osmotic pressure of that much concentration solution of aluminum chloride? So aluminum chloride is what? Aluminum chloride is a strong electrolyte, right? So aluminum chloride will dissociate into, this is a solid, and that is going to dissociate into Al3 plus aqueous plus 3Cl minus aqueous. So the total number of ions that I am forming here is equal to 4 ions. So I'm forming 4 ions in there, and that is going to be I. I want to calculate the osmotic pressure. I know that I is for concentration, R, and T. Okay, so I have to change the T into Kelvin. So T is 0 degrees Celsius plus 273, so it's going to be 273 Kelvin. I'm done with the T. For the R, again, I'm going to use the R that has a torr unit, so it's going to be 62.4. This is going to be liter torr, so that my osmotic pressure has units in torr. Okay, and I know what's the concentration, so it's a direct substitution in here. Everything will be wrong if you don't know the number of ions that you have in the solution. So please make sure that you draw the dissociation equation and show your ions forming so that you can count your ions properly. So this is liter torr K mole. This is it. And then you multiply this by 273 Kelvin. And the answer here is going to be 3407 torrs. Okay, so that is your answer in there, 3407 torrs. Or if you want to express it in sig figs, it's going to be 3.4 times 10 to the 3 torrs. Another example, a solution prepared by dissolving 20.0 milligram of insulin in water and diluting to a volume of 50 mils, because the concentration is in moles per liter. Gives an osmotic pressure of millimeter Hg, so I have to change this into torrs as well. And you do have your temperature. What is the molecular weight of insulin? So they need now the molecular weight. So let's lay down our formulas. We know that the concentration, okay, so I know that the concentration is equal to the moles divided by the volume. This is one thing, right? And I know that the moles is equal to the mass divided by the molecular weight is equal to I times the concentration times R times T, right? So can't I make a relationship between the concentration and the molecular weight? Well, I know that the concentration is equal to what? Is equal to the moles divided by the volume, right? Okay, what is moles? Moles is equal to the mass divided by the molecular weight. So I know that concentration is the mass divided by the molecular weight, okay, divided by the molecular weight times the volume in there. So we're going to do molecular weight times the volume. So this is the new relationship in there where I can substitute the value of m in the equation by the mass divided by the molecular weight times the volume. So let's put that. That is equal to I times the mass divided by the molecular weight times the volume times R times T, and this is equal to the osmotic pressure. I need the molecular weight, you guys, so we can do a cross multiplication. So we can do a cross multiplication over here, and we say that pi molecular weight V is equal to I times the mass times R times T, divide by pi V, divide by pi V. So pi V over here. So we get a relationship of the molecular weight that is equal to I times the mass times R times T divided by pi V. So you can add this to the new equation sheet, for this chapter. So I is equal to the mass times R times T pi times V. When do we use it? When we are asked to calculate the molecular weight. This is the easiest way. You just put in the formula in there. Now we know that pi given to be in millimeter Hg, right? So we have to change this Hg. So we have to change this into torrs, or you can change it into atmosphere. So I'm going to change to torrs. Again, you can change into atmosphere. So if you do that, R needs to be used in atmosphere. I'm going to use it in torrs here. So I'm going to do 12.5 millimeter Hg. Do the conversion units. I know that 1 torr is equal to 1 millimeter Hg. And this is how I can simply get that to be in torrs now. Okay? So once you get it in torrs, we can directly substitute the molecular weight. That is equal to 1 times one times the mass in there. So what was the mass? The mass is 20 milligrams, right? So 20 milligrams. I have to change that into grams. So it's going to be 20 times 10 to the minus 3 grams. You have to divide by 1,000 to go from the milligrams to grams. I'm going to multiply this by R, which is 62.4 liter liter torr. Okay, so that is liter torr divided by the mole times K times the temperature, which is 300 K, divided by the osmotic pressure that we just calculated, times the volume, and the volume has to be in liters. It's given 50 mils, so it's going to be 50 times 10 to the minus 3 liters. Do your calculation, and that is equivalent to 599.04 grams per mole, and this is going to be the molecular weight. Another example, this is the hardest it can get, by the way. because this one requires multiple steps. What is the osmotic pressure for a 5% weight by weight sugar? So they give you the molecular weight for, or the molecular formula for the sugar. We can get the molecular weight for that. So we can calculate the molecular weight for the sugar, which is 342.3 grams per mole. Just look at the periodic table, you guys. For the mass of the carbon, the hydrogen, and the oxygen, multiply them by their coefficient, add them up, and you should get this value over here. So the solution, okay, so they want the osmotic pressure. If the density, they give you the density and they give you the weight percent. So from the weight percent, we can get the concentration. I'll show you how. And from the density, we would need the density because we would need the volume. Okay, so let's start. What does 5% weight by weight means? 5% weight means that I have 5 grams of the solute. This is what 5% weight means. It's 5 grams of the solute. Look at the formula for the weight by weight. It says that the mass of the solute divided by 100 grams of the solution. So you know what is the mass of the solution. So the mass of the solution is 100 grams. This is the mass of the solution. So you have the mass of the solution and you have the mass of the solute. Okay, pay attention to that. So you're given the mass of the solution, you are given the mass of the solute. So the mass of the solute, we can use it to calculate the number of moles, but the mass of the solution, we can use it to calculate the volume because we already know the density of the solution. The density of the solution, that is equal to the mass of the solution, okay, divided by the volume of the solution. Okay, guys? So mass of the solution divided by the volume of the solution. We can get the volume of the solution this way. Why do we need the volume? Because we want to calculate M. We want to calculate the concentration. And the concentration is the moles divided by the volume. So if we have moles, we know that moles is equal to the mass divided by the molecular weight. We already know what the mass is, which is 5 grams, because this is the moles of the solute. So it's the mass of the solute. We already know the molecular weight, we can get the moles, right? And then I know that the concentration is equal to the moles, which we're going to get it from up. And we're going to divide this by the volume of the solution. So this is why, guys, you need the density in order to get the volume of the solution in there. So the volume of the solution is equal to the mass of the solution divided by the density of the solution. Okay? So you have both in there, mass divided by the density. So I already know what's the mass of the solution is, which is 100 grams. Density of the solution is given, how much is it? It's 1.02 grams per mils. So it's 1.02 grams per mils. And I can get over here the volume in mils. This is it. This is going to be in mils. We can change that into liter. So it's going to be 98.04 times 10 to the minus 3 liters in there. So we got the volume of the solution. We can, before substituting it, let's go ahead and calculate the moles in there, which is 5 grams divided by the molecular weight, which is 342.3 grams per mole. And that is the grams, and grams cancel out, and that is equivalent to 0.015 moles. Now I can take the moles here and I can substitute them down. 0.015 moles divided by the volume of the solution that we just calculated here, which is 98.04 times 10 to the minus 3. Pay attention, it has to be in liters because this is the unit for the molarity, and that is going to be 0.153 molar. Okay, so I got M. I know it's sugar, right? So I is going to be 1. So I know that, and I know each one of those. So I can now substitute my osmotic pressure to calculate the osmotic pressure there. I can do my substitution. So I is 1 multiplied by the concentration that I just got, which is moles per liter, multiplied by the R gas constant, which is the 62.4 liter torr mole Kelvin, multiplied by the temperature, which is 298 Kelvin. How did I get this? You are given the temperature in Celsius, you guys. This is 25 degrees Celsius. So the temperature is equal to 273 plus a 25, and that is equal to 298 Kelvin. So we're going to substitute that here. Do your calculations, and the osmotic pressure now is 2845 torrs. The last topic is colloids. Colloids are homogeneous mixtures, and they are made up of 2 or more components, and there is more of one component than the other in the mixture. Colloids are made up of 2 parts, a dispersing medium and a dispersing phase. So the dispersing medium of the colloid, this is similar to the solvent in the solution, okay? It's similar to the solvent in the solution, so let's write this down. That is similar to solvent in solution. So this means that the substance is present in a colloidal dispersion in a large amount, because it's kind of like a solvent. So this is what it's a dispersing medium. And then the dispersing phase, what is that? This is similar to the solute of a solution. So that is similar to solute of the solution, or solute in the solution. So that is the substance present in a colloidal dispersion in amounts less than that of the amounts of the dispersing medium. So the dispersing medium is similar to a solvent, and the dispersing phase is similar to a solute. Okay, so always the dispersing phase is in the dispersing medium. Now, if we look at particles in the colloid, these we cannot see them. They cannot be seen. They are suspended in the solution. They are not precipitated. They cannot settle due to gravity. Since they are particles in the solution, they scatter and reflect light, which we call it a Tyndall effect. This is why colloidal solutions, they do appear cloudy because of the particles in there that are suspended in the solution. And as we said, like these particles, they do scatter light. So if you take a light source and you shine it through a colloidal solution, this is a non-colloidal solution, this is just water, versus a colloidal solution, like let's say, for example, milk. Milk is a colloidal solution. Milk is not a transparent. Milk has particles, has a dispersing phase in there that is suspended in the solution. So if you shine the light in there, you're going to see a visible path of the beam of light. Why? Because light is scattered in all directions in there. So you're going to see that visible beam path of the beam of light, indicating a Tyndall effect that is well known in colloidal solutions. Which of the following does not experience Tyndall effect? Fog. Fog is made up of colloidal particles, smoke as well, milk as well. But salt water, no, salt water, it's ionic. The salt, which is the Na and the Cl ions, these are completely soluble in water. So salt ion is a regular solution. It is not a colloidal dispersion. So salt water does not experience any Tyndall effect. Dialysis is the process in which the solvent molecules and other small molecules, so here we do have a dialysis tube. The dialysis tube does have pores, and the pores are larger than the pores of the osmotic membrane. So the dialysis tube allows the exchange of small molecules and ions from the tube into the solution. Okay, so we would have an exchange of these ions in there. Why do we use dialysis tubes? We use dialysis tubes to separate the small particles from colloids. So here we have a colloid, we have a small particle that we want to get rid of. So we put them in dialysis tubes. Now the tubes they are different, they have different size pores. So depending on the size of the pore that you choose for the dialysis tube, we can get rid of those small ions and small molecules, and they can get out of the dialysis tube and be in the solution. This is the process that normally is used to clean the blood of people suffering from kidney malfunction.